Hello to everyone. Welcome to the course on numerical linear algebra and application. Today we are going to have 12th module of this course. In the 12th module we have the contents, how the matrices would have got an applications in the real life systems of differential equations, integral equations of various contexts such as control systems, fluid dynamics, image processing, sound waves, algorithms, and so on and so forth. Today, in this 57th lecture of this course, we would like to see some applications pertaining to the differential equations, how they would be applicable, and ultimately you will end up with matrices, and how you could able to solve the matrices in order to analyze the pertinent physical parameters of interest. So in the application of matrices, the first problem let us consider is critical buckling load. As a matter of simplicity, let us consider a long sledger rod of length L as shown over here. So this is L. The rod is clamped at one end and hinged at the other end. So this is the wall hanged. At one end and hinged at the other end. At the hinged end, the rod is compressed axially by a force P, remains below a certain critical load P critical. The rod will remain straight like this. However, for P greater than PCR, P critical, the rod will deflect from the straight configuration or buckle. Straight configuration or buckle. We would like to determine both CR, PCR and shape of the buckled configuration. So this is how the load is applied over here, and this is the hinged end, it is the clamped end, and this is the length of the rod. Let capital X denote distance along the length of the rod. So this capital X is the distance along the rod. When X happens to be 0, corresponding to the clamped end, so when X is equal to 0 means corresponding to the clamped end, like the one where you did it over here. Here, in this space, X is equal to 0. Further, let Wx denote the deflection of the rod from its straight configuration. Let Wx denote the deflection of the rod from its straight configuration. The differential equation for W is d square W by dx square times of Ei into d square W by dx square plus d by dx of P into dW by dx is equal to 0. Where E is Young's modulus, and I is the moment of inertia of the rod's cross section. E is Young's modulus and I is the moment of inertia of the rod's cross section. I is the moment of inertia of the rod's cross section. At the clamped end, the rod can neither deflect nor rotate. So that is no deflection or no rotation. Where E is Young's modulus, I is the moment of inertia of the rod's cross section. At the clamped end, the rod can neither deflect nor rotate. So you will have W is equal to 0 is 0, dW by dx of 0 is equal to 0. At the hinged end, the rod cannot deflect and no bending moment can be imparted. So you will have W of L is equal to 0, d square W upon dx of square of L is equal to 0. Introducing the non-dimensional independent variable x is equal to capital X by L, the equations 1, 2 and 3 becomes like this. W4 plus lambda times of W double prime is equal to 0. So W0 is equal to W prime 0 is equal to W of 1 is equal to W of double prime is equal to 0. Where prime denote differential equation with respect to x and lambda is equal to PL square by EI, where lambda is equal to PL square by EI. To approximate the solution of equation 4, we will start by dividing the interval 0, 1. So 0, 1 into 3 equal sizes. So that is h is equal to 1 minus 0 by 3. So then we will assume that W of x is approximately equivalent to I is equal to 1 to 5 Ci times of pi I of x. That is Ci times of pi I of x. Where the Ci's are constants to be determined and phi's are known as basis functions. So they are all basis functions. For this problem, we will use the following equations. That is, phi 1 of x will be equivalent to 27 times of x square 1 minus 2x. That is 0 less than or equal to x less than 1 over 3. And this is 6x minus 1 times of 3x minus 2 whole square. It is 1 over 3 less than or equal to x less than 2 over 3. Third one is 0 elsewhere. So therefore, pi 1 of x is nothing but 27x square times of 1 minus 2x for x lies between 0 and 1 by 3, and pi 1 of x is equal to 6x minus 1 times of 3x minus 2 whole square when x lies between 1 by 3 to 2 by 3 and 0 elsewhere. So pi 2 of x is nothing but 3x square 3x minus 1 when x lies between 0 to 1 over 3, and x minus 1 over 3 and 2 minus 3x whole square when x lies between 1 over 3 to 2 by 3, and this is elsewhere. So therefore, you do get pi 3 of x will be equivalent to pi 1 times of x minus 1 over 3, pi 4 times of x is equal to pi 2 times of x minus 1 over 3. So ultimately this pi 5 of x, it will be equivalent to 9 times of x minus 1, x minus 2 by 3 whole square, and x lies between 2 by 3 to 1 and 0 elsewhere. Graphs of these functions are shown in the below figure. The function pieces that are used to construct these basis functions are called Hermite cubics. So you will have Hermite cubics, you see here. Now this is the line, so you will have like this, and this is the one you do have. Point 1, point 2, point 3, point 4, point 5, point 6, point 7, point 8, point 9, etc. in this side, 0, point 2, point 4, point 5, point 6 on this direction. Next multiply the differential equation in 4 by pi j of x, that is pi of j of x for j is equal to 1, 2, 3 up to 5, and integrate the resulting expression from x is equal to 0 to x is equal to 1. So we will have 0 is equal to integral 0 to 1 w power 4 x plus lambda times of w double 4 of x multiplied with pi j of x dx. So ultimately this turns out to be integral 0 to 1 w for 4 of x pi of j of x dx. So if you integrate now the integral containing w4 by parts, so that is first function into integral of second function minus d by d of first function into integral of second function. In this fashion, if you do, you will end up like this: 0 to 1 w double prime of x pi double prime jx minus w prime of x pi prime of j of x dx plus w double prime of x pi j of x plus w prime of x pi j of x minus w double prime of x pi prime of j of x from 0 to 1. Since pi j is 0, pi j of 1 is 0, pi j prime is 0, for each j and w prime of 1 is equal to 0, the second term on the right hand side of equation 6 is identically 0. So consequently you do have this equation, that is integral 0 to 1 w prime of x pi j of double prime of x minus w prime of x pi j prime of x, that is dx is equal to 0. Equation 7 is called the variation or weak formulation of equation 4. Substitute equation 5 into 7 and rearrange the terms leads to the system of algebraic equation like this. You will have AC is equal to lambda times of B of C, where lambda is the scalar and C is the C1, C2, C3, C4, C5 matrix S transpose. So you will write A is equal to this matrix, that is A is equal to integral 0 to 1 pi I double prime of x pi double prime of j of x dx. So you will have the matrix like this, 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 matrix like this. So this is actually a banded matrix, 1, 2, 3 band matrix. So this is the example how we would able to turn up this matrices. So therefore B is nothing but integral 0 to 1 pi I prime of x, pi j prime of x, which turns out to be of this matrix. Phi of a matrix. We are interested in non-zero solutions for the vector C, as these corresponds to deflected configurations for the rod. In particular, we want to determine the smallest value of lambda, as this corresponds to the smallest axial force for which equation 8 has non-zero solutions. So thus we have transformed this equation, what was called boundary value problem, into eigenvalue problem. So how actually BVP is converted into eigenvalue problems? Because matrices appear on both sides of 8, this is called a generalized eigenvalue problem. So what is the reason that how the boundary value problems will be converted into the eigenvalue problem is to reduce these matrices size and to get into the what you call as sparse matrices. To proceed with our analysis, note that B is symmetric positive definite. The matrix B is a positive symmetric positive definite. If we let L into L transpose, that is L into L transpose denote the Kuleske factorization of B, and then C is equal to, you define as L inverse A times of L transpose over inverse, and Y is equal to L transpose of C. The generalized eigenvalue problem AC is equal to, that is A times of C is equal to lambda times of BC, becomes the standard eigenvalue problem, that is Cy is equal to lambda Y. In this instance, you get a matrix of this form. So that is 1, 2, 3, 4, 5 rows and 5 columns. Applying this inverse power method with q is equal to 0, a randomly selected initial vector and a convergence tolerance up to this value, that is 5 into 10 power minus 6. So which produces lambda is approximately into 20.3146, and P corresponding error is, that is the PCR is, critical value is 20.3146 EI upon L square. And further you can write this matrix Y is equal to 0.101824, 0.206840 and 0.903036 minus 0.052444 minus 0.358643 all transpose. Solving the equation Y is equal to, that is Y is equal to L transpose C, and normalizing the result to unit length in the L2 norm, that is in the L2 norm, so you do get a matrix of this form, that is C is equal to, so that is 0.117527, 0.511028, 0.195196, and minus of 0.192401, minus of 0.806175. So you get a figure like this. So non-dimensional length, and this is the deflection. So you will have a pictorial representation like this, and this is the x-axis, and this is the y-axis. The deflection of clamped hinged rod when loaded with its critical buckling load is P critical load, that is PCR is P critical load. QR factorization using rotation matrices. Definition: let I is less than j, the orthogonal matrix Pij, which is identical to the identity matrix with the exception that Pii is equal to Pjj is cos theta, and Pij is equal to minus Pji, which will be equivalent to sin theta. The name rotation matrix arises from the geometric fact that Pij represents the rotation of the ith and jth axis about the origin of the coordinate system by an angle of theta. For a later use, it is important to note that pre-multiplication of an arbitrary matrix M by Pij affects only the ith and jth rows. In particular, ith row of Pij M is equal to cos theta, ith row of M plus sin theta, jth row of M So you get the matrix of this form, that is jth row of Pijm is minus sin theta, ith row of m plus cos theta is jth row of m. For an n by n matrix, we make n minus 1 passes through the matrix, with each pass zeroing out a specific element below the main diagonal. Thus, in the first pass, P12 is chosen so that P12 AI has 0 in 2 column 1. Next, P23 is chosen so that P23P12P has 0 in the third row of the second column. P3 is chosen so that P34, P23, P12, P2 has zeros in the third column, in the fourth column of third column, and so on. Finally, Pn minus 1n is chosen so that Pn minus 1n, P3, etc. is an upper triangular matrix. Hence, the Ri is equal to P of n minus 1 comma n, P34, P23, P12, Ai. To examine the details of this factorization scheme more closely, let you write this matrix. Ai is equal to, this is the matrix, you do get this matrix, and this is the matrix B, and this is the matrix B, and these are all zeros. For notational convenience, let the cosine and sine values associated with the rotation matrix Pij plus 1 be denoted by Cj and Sj respectively. Carrying out the multiplication P1 to Ai, we find that this is the matrix, and this is the matrix, and these are the zeros, and these are all zeros. We now want to choose C1 and S1 so that is minus times of A1 S1 plus B1 C1 is equal to 0. One solution of the equation is which also satisfies the fundamental trigonometric identity, that is C1 square plus S1 square is equal to 1. So you will have C1 is equal to this matrix, that is A1 upon A1 square plus B1 square, and S1 is nothing but B1 upon A1 square plus B1 square. With C1 and C2 S1 selected so that minus A1 S1 plus B1 C1 is equal to 0, note that A1 appears on the right hand side of equation 9 in the first row, first column only. The precise location of A1 in the matrix AI, we may therefore overwrite A1 with the expression like this. This is the matrix, you do get it. So in a similar manner, we would like to save the first two elements in the second column of P1 to A in place of B1 and A2. Unfortunately, to calculate these elements, both B1 and B2 are required. However, if we save the current value of B1 in a temporary variable, so we could able to manage these values. Finally, we save the value of B12 in the variable t and then overwrite B2 with the quantity B2. So therefore, ultimately we associate with the next matrix as we spoke in the previous case. So the calculation required by all subsequent passes in the factorization step are identical to those indicated for the first pass. With two exceptions. First, we of course need to increment the subscribers for each new pass. So you would have like this, that is C of j is equal to Aj upon Aj square plus t square under square root, and S of j is equal to t upon Aj square plus t square under square root. So if you look at this, the coding for this, the matrix is save B1 in the temporary variable as a t. Then what we do is for j is equal to 1 to up to n minus 1, let r will be Aj square plus t square, and we will be computing, that is Cj is equal to Aj upon r. And this S of j is nothing but t upon r, and override this, and we will make into Tj plus Aj plus 1 S comma j. And when you overwrite this Aj plus 1 with this matrix, we will overwrite the save the Bj plus 1 in time t and make an n. So the previous loop ends over here and the final loop ends over here. The first line in this pseudocode has been included so that the first pass can be handled in the same manner as all of the later passes. The final two statements have been placed inside a conditional statement, since during the last pass through the matrix there is no element, that is b of j plus 1 will be equivalent to b of n, or and overwrite it. So after having had this the terminologies, let us look at into the some few examples how we could able to apply this matrix. Let's consider this matrix 3 by 3 matrix. Let's consider this 3 by 3 matrix. For this example we have, so this is the value of A1 and this is the value of A2 and this is the value of A3 and these are all values of B1 and B2 is these values B2 and rest are all zeros. Look at this. To prepare the first pass, we set t is equal to b1 is 3. We then calculate this value r is equal to a1 square plus t square under square root, that is 5, and c1 is equal to a1 by r, that is 4 by 5, and s1 is t by r, that is 3 by 5. And set a1 is equal to r is 5. Next we set t is equal to b1 is equal to 3 and then calculate these values. b1 is equal to tc1 plus a2 s1 is 3 and a2 is equal to minus ts1 plus a2 c1 is equal to minus 1. Finally, we set t is equal to b2 minus 1 and calculate these values. That is b of 2 is equal to tc1 which is minus 4 by 5. The second pass starts with the calculations, that is r is equal to a1 square plus t square under square root. So you get it as square root of 2. So C2 is equal to, that is A2 upon R, which is minus 1 by root 2. So S2 is equal to T upon R, that is minus 1 by root 2. After setting A2 is equal to R root 2 and T is equal to B2 minus 4 by 5, we then calculate B2 is equal to TC2 plus A3S2, that is minus 11 by 5 root 2. And we write this matrix. The results of our factorization of A are therefore, that is A1 is equal to 5 and A2 is equal to root 2, A3 is equal to minus 19 upon 5 root 2. Similarly, you write B1, B2 and you write C1 and S1, C2 and S2. So you get all these values. We will examine how to use these values to compute the product, that is R of 0 times of Q of 0. Bringing all the information together, it follows that to obtain the product, that is Ri Qi, we need to perform the following operations. Overwrite Aj with, that is Aj Cj plus Bj S of j, and overwrite Bj with Aj plus 1 Sj and overwrite Aj plus 1 with Aj plus 1 comma C. For a j is equal to 1, 2, 3, etc., note that the Ej do not play a role in any of these computations. The product, that is R of 0 times of Q of 0. The first set of calculations leading to the product R of 0 Q of 0 yields, that is A1 is equal to this value and B1 is equal to this value, A2 is equal to this value. The second set of calculations then gives A2 is equal to this 0.3, B2 is equal to this, A3 is equal to this, and ultimately you will end up with this matrix. So A of 1 is equal to R of 0, that is Q of 0, which is equal to this matrix 5.8, 0.848528, 1, and this matrix. So you get a 3 by 3 matrix. Anyway, this is also a banded matrix. You see our zeros over here. This is also a banded matrix, as we could see from this. So the overall idea is, when you are applying the differential equations for real life systems, you do end up with the matrices. So how you do factorize these matrices in order to find out the best approximations. This is one of the examples which you have seen. In the next lecture, we will see some more examples. Thank you very much for listening to my lecture today. Thank you once again.